Hi guys, I'm here right now to talk to you about how we use gates to implement logic. So first, what I want to do is focus in on this symbol. And this is the electrical engineering symbol for a transistor. Right over here. So, uh, how and what it's doing in this piece of logic, as I release that, oh, good way, is it's being a inverter. That means that it's implementing not. So V out is not, okay, V out here is not V in. Okay, equals not V in, to use that. Okay, there's a lot of different ways, but that's the one I've been teaching lately. Okay, so why is this true? Well, right down here is, oh, give me that pen back. Right down here is the symbol for ground. Anything hooked to that guy is drawn to 0. So this side of the wire is 0. Now, anything up here, okay, let me actually get out of that. Anything out here, this VCC thing over here is actually the power. It's full charge coming from whatever, the power side of the battery or the generator or whatever we're using, and anything over here is going to be a 1. Okay, so V in, okay, so if V in is 0, if V in is 0, the gate is closed. Remember what we said, transistors are gates? That means that this guy is, the transistor is a resistor. It's totally stopping any connection with the 0. So the V out connects with the 1. But let's say V in is 1. Okay, so V in wants to be 1 right now. That means that the transistor is open. Now, what happens is the 1 and the 0 now are connected on a direct line. But that's what this resistor is doing. That zigzag line is a resistor. And what will happen is that the connection to the 0 is a lot stronger. So V out will actually end up as 0. So when V in is 0, V out is 1 in green. When V in is 1, V out is 0 in blue. Now, one thing is, it's really not great for the circuit when V in is 0. Because what happens is when you have power on one side of a resistor and ground on the other side, I mean when V in is 1, it's a problem. Okay? When you have power and ground directly connected to each other, that's called a toaster. And what happens is this guy gets hot. So this is called, but as long as it's 0, it's fine. But when it becomes, but when the V in is 1, when the V out is 0, this guy generates heat. And if you throw too many of these little guys, all working at once, into a circuit, or into logic, you can have problems with your chips melting, or the insulation around them melting, or basically your computer turns into a toaster. Computers run hot. Now, one solution for that is instead of using this kind of logic, what they use is they put in the place of this guy another transistor with not V in coming out. So when V in is 1, this guy, the 1 is blocked. And when V in is 0, the 0 is blocked and the 1 is open. And that works, but the problem is you need twice as many wires, because you have to keep, every wire has to have a not wire as well. And this is called CMOS, complementary, because you have the complement, not V in, as well as V in. And that uses a lot less power, right? You don't add, because it's not being a toaster very often. But there's still one time. Remember, if you go back here on the power circuit, right over here, if you go back and remember, the yellow area is where, when V in turns from 0 to 1, you're in that yellow area. And both guys are sort of half transistors, sending half the power through. And then you do get, so when you switch from 0 to 1, you still generate a certain amount of heat. So the heat in CMOS occurs entirely when things change. Now that's why CMOS is great for something like BIOS, where things don't change very much, where the vast majority of the circuit stays the same all the time. It's basically ROM. But in fact, you can build circuits. Now, the problem, of course, one of the problems is that as circuits get faster, the switching happens more and more, and the advantage of CMOS starts to disappear. Okay, so enough, but either way, the basic thing is this guy generates not V in. This circuit is a NAND. When V1 and V2, okay, so when V1 and V2 are both on, V out becomes 0, gets cut to ground. Otherwise, if they're not both on, V out becomes 1. So it's not and, is what this circuit is. And similarly, this guy is a NOR. Okay? When V1 and V2, when V1 is on, there's a connection to 0 and V out is 0. When V2 is on, there's a connection to 0 and V out is 0. But if neither are on, then V out has to be 1. By the way, when using CMOS, when using complementary logic, what we end up doing is there's a series circuit, and the complement is a parallel circuit. And the opposite of this parallel circuit will be, I think, a series circuit. So there's a lot more. So CMOS is a lot more complicated to make. Tends to take up more space on the thing, but like the power consumption issues sometimes are the most important thing, because it doesn't. If you build the tiniest chip in the world and it immediately catches fire on use, that's not so useful. Uh, Other people have talked about the switching is, the less in CMOS at least, the less problems you'll have, the less heat you'll generate. So faster switches are better not only because they're faster, but because they're less heat generating. The also the complementary logic. What am I saying? Okay, another idea here. So your 3.1 in the book, which is, where is it? All right. And where's my course marked? Here. This is on page 136 of your book. So this diagram I just took. So we're going to see a lot of diagrams taken from the book now. So let me get this thing so I can page through the book a little easier. So that's how we do it with logic. The last thing I want to talk about is we represent what we don't usually, unless we're doing chip design or something, if we're just designing a circuit, we instead use these symbols. Not this triangle circle, NAND, NOR, and OR. And they even have little truth tables down there for the whole thing. So this is the symbology we use when in figure 3.2. I'm going to give you one more symbol a little later, when we want to refer to not NAND and an NOR, and I'm going to stick that right into the notes for you. I get hit on my shoulder in the notes, but so there we go. There, right in the notes is my shoulder. Now, so that's going to give you, but you can always look up the figure in the book. Was page in the book, page, things in the way, 137. So 136. So these are from the book, pages 136 and 137 is where you can find these diagrams without my shoulder in the way. And that's the beginning of what digital logic is about.